we are here for the second last session of this machine learning and deep learning program, which is going on for last 4 days. Today is the 5th day, and today we are at the 8th lecture. And for 8th lecture, I would like to inform you all participants that we have Dr. N. Sudha, a very senior professor from School of Computing, Shastra, deemed to be university, and she'll be talking about on GYAN, as I mentioned in the schedule, that is Generative Adversarial Neural Network. So stage is to Madam Dr. N. Sudha to start the presentation.
Thank you, sir. Good afternoon, everyone. So the presentation is on generative adversarial networks, and I am Dr. N. Sudha, professor from School of Computing of Shastra University. Let me briefly introduce about myself in this slide and move on to the technical presentation. I had my education, master's and PhD from IITs, and then BE from Madurai Comrade University. And in terms of work experience, I have a mixed academic as well as the industrial R&D experience, and academics mostly for more than 15 years. And industry, I worked in Exmo Semiconductors, which is based in UK, and also in Tata Elxsi, both are R&D division I worked in. And then currently I am in Shastra University for the past 3 years. Let us first introduce what are GANs, Generative Adversarial Network, I said. So what is adversarial? When in the past you must have learned this convolutional neural network and recurrent neural network. Those are single neural network. But here, adversarial in the sense it has two neural networks competing with each other, fighting with each other. It's like you must have learned in artificial intelligence. Generative in the sense it will generate images when you must have learned this convolutional neural network and a recurrent neural network, where they are the single networks and they are not useful for generating the images. They are mainly useful for classification, but generative adversarial networks are useful for generating images. And adversarial in the sense it is actually having two separate networks, one fighting with the other. So it is in the competitive mode. Both the networks are in the competitive mode, one fighting with each other. So it is a system of two networks competing against each other, and it is introduced by Ian Goodfellow in 2014, and it is mainly used to learn to generate the new samples that are similar to the training data. So once then the network is trained with some kind of data, it will be able to generate new samples similar to that. And it can also translate the samples. Next. So this is the basic structure of generative adversarial network. So it has one generator, which is it can be a fully connected network or even a convolutional network. And there is one more network called discriminator, and this receives the actual real training data and also the generated image, and then it compares and say when the real data is presented, it says it is real, and when the generated data is presented, it has to say it is a fake data. And the generator, you will generate the images, and the input to the generator is the random noise. So in the basic generative adversarial network, the input to the generator is the random noise, and it will generate the image that is close to the training data. So when you consider the generator before and after training, before training, when the input is a noisy image, then the output is also another noisy image because it is not trained properly. But after training, what it does is it will generate the image close to the data set it was learned, it was trained for. So if you are training with some handwritten data sets, handwritten digit data set, then the output will, after some point of time, after getting trained, it will generate something close to that, even when you input a noisy image. So it is very useful for data augmentation, which is very much necessary in deep learning, where we want to have a large data set. We want to generate a large data set. In that case, you can generate samples like this. And how about the discriminator? The discriminator is a simple classifier. It will not generate an image. It will try to classify the image. So when it receives the real data from the data set, it will say it is 1. And when it receives a fake image from the generator, then it will say fake. So it will be, the output will be either 1 or 0. It is trained for that, like that. So how to train this generative adversarial network? It has a flow. So the training of the generative adversarial network means it is we are training the generator, because afterwards, once the network is trained, we use only the generator and not the discriminator. Only during the training, the discriminator is used. So the discriminator is trained separately and the generator is trained separately. So we want to expect the generator to produce the real images. So it is set the expected output of the discriminator to 1 when training the generator. When you train the generator, the discriminator output, we want to keep it 1, because the generator always says I am generating only real data. Only the discriminator always discriminates the generated output from the real data set input. In that case, when you train the discriminator, the generator's output is the generator's output is considered as a fake, which is the expected output will be 0. But when you train the generator's output is expected to be a real output, so it is 1. So how will be the training loop in this case? First, you said the discriminator trainable. So we have to do the training alternatively. The discriminator and the generator are trained alternatively. So that first you set the discriminator trainable, and then you train the discriminator with the data set as the real images. The real images are given to the discriminator. If you give the real image to the discriminator, you set the output to be 1. And when you view the fake image from the generator, you set the output to be 0. That's how you do the discriminator training. So this, so while doing the training while training the discriminator, your generator weights will not be updated. Only the discriminator weight will be updated. But we cannot keep on updating the discriminator alone. So after one iteration, you can move on to the generator for training the generator. So the third step is you set the discriminator not trainable, okay, and train the generator. So the generator is trained, but while training the generator, you keep the discriminator, you attach the discriminator, but the discriminator weights are not changed. It is not trainable. Only the generator we are training. Feed the latent input, that means latent samples, that is a noise sample. And you set the output to be 1, the expected output to be 1, and your training is nothing but back propagating the error. That is the normal error back propagation algorithm is applied for that. So these 4 steps are repeated. That means for one iteration, the discriminator is trained, and the other iteration, the generator is trained. So that's how it goes on. So the loss function will be like this. It is called the minimax loss function because one is trying to minimize the loss function and the other is trying to maximize something. So when you take the discriminator, it tries to maximize this function, and this function has both components. One is for the discriminator, and another is for one is for the real image, and another is for the fake image. That is for the discriminator. So the loss function has both the real image related term as well as the fake image related term. But when it comes to the generator, you are trying to minimize this loss function. This loss function is it is only belonging to the loss function, which is where the input is the fake image. Okay. So the discriminator tries to maximize this, but the generator tries to minimize this. That's why it is called a minimax, because it's adversarial one. So one person in the adversarial games like chess, one person wants to maximize his score and tries to minimize the other score, that is the opponent's scores. So that's why it is called a minimax function. So here d of x represents the this is the probability that the real data, x is the real data. So when you input the real data, what is the probability, the estimated probability of the output? And ex is the expectation, which is we are taking the expected value over all real data instances. And G of Z is the generator's output, which is the fake image. And D of G of Z is the probability that the fake instance is real. So this is related to the generator's output. This is related to the actual data set input. And EZ is again the expected value over all random inputs to the generator. Okay. So when you look at when you give noise and to the generator, and the training is done with the handwritten data set, then you will get some images like this. These are the generated images. When you run this, I think it is I have to come out of this, but these are the generated output finally, but initially you will have the random inputs, the images, whatever it is generated, they are all noisy image, and slowly after with iterations, it tries to learn what the discriminator expects. So the generator tries to learn what the discriminator expects. That means it will try to generate the outputs that are very close to the real data, which was input during the training. So these are some of the generated outputs. You can see that it is more close to the handwritten characters, and you can even identify some of these characters. Most of these characters you can identify. So that is the basic GAN, but there are many variations to this basic GAN. One is the conditional GAN, and in the conditional GAN, what the basic GAN does is when you input a noise, you will get a fake image as output. but we don't have any class information associated with the fake image. But if you want to have the class information also associated with the fake image, we want to generate, suppose if you consider the digits, we have around 10 classes from 0 to 9. So there are 10 classes. So if I want to generate only 5, then I want to give the input, the class input also to the generator along with the noise. So not only the noise, but also the class input is given to the generator. So if I give 5 as the input to the generator, then the sample output you generates will be close to 5. So that is the conditional GAN. We are giving some condition to the generator to generate a particular class of image. And during training, the class information is also accompanied. It's not only the dataset images, but also the class information is also accompanied. So that's how the training is done, and during the training phase for the discriminator as well as the generator. Once it is trained, then if you give the class label and also the noise, then it will give the sample output which is related to that particular class. That is the conditional GAN. And there are many applications for this generative neural networks, GANs. One important application is the image translation. What it does is, if you give a zebra image, it will be translated to a horse image. And if you want to translate from horse to zebra, so here the input is again a reasonable image. So in the basic GAN, you have the input as the noise. In the conditional GAN, you have the input as the noise as well as the class information. But in the image translation application, you have the input as a image itself, and it is translated to another image. That is the image translation. It is also useful for photo editing, because the image translation, if you give the image of one person, you can convert this person into a female version, and also the smiling version like this. So it is photo editing, it is useful, and also to predict the aging. If you are given the image, if you are giving the image like this, and also that you want to see the image of the person in 30s or 40s or 50s. Now he is in 20s, and then you can also associate that that information also, that is more or less like a class label. You can give the age information also in 20s, 30s. So it will generate the image. So you can predict how the person will be like in a particular age. So that is the image to image translation. So the image to image translation, the network is called the pix to pix, because each pixel is transformed to another pixel. So that is the pix to pix translation is done. So the generator should be a encoder decoder network, because the input is image and the output is again an image. So if you want to do the segmentation in the case of autonomous driving, then the scene is given, then you get the segmented output. So this is also one kind of image to image translation only. You are giving the image, RGB image, you are getting the segmented output. So the generator is a encoder decoder network, and the conditional GAN is useful in this case, because conditional GAN is always the input is a reasonable input, we not just a noisy input. So you can have applications like aerial to map generation. So the aerial image, in the case of remote sensing, the aerial image is given and the map is generated. and some edge image is given, the photo is generated. So these are some applications of this pix-to-pix network. And apart from this pix-to-pix, there is something called cycle GAN. It is also a image-to-image translation, but well, here we are not giving the paired image for training. In the pix-to-pix, we give the paired image. Like if you want to generate a output image out of the edge image, then in the pix-to-pix, what you do is you are pairing this images, and while training, you have to give the input image like this and the output image, the corresponding output image has to be given. But in it is very difficult to generate in many cases. We want to, suppose if you are having the photographs and if you want to generate the painting of that particular photos, then we have to generate for training. We need to generate the pairs, isn't it? But in many cases, it's very difficult. Even in the autonomous driving case also, if you are given the RGB image and if you want to get the segmented output, so that pairing can be avoided in this kind of cycle GAN. You can view the set of images, RGB images, and also a set of output images, or some painting. So if you use this as input and that as set to output, then the cycle GAN will can learn how to generate a new pair from that. So that is called the cycle GAN. So the cycle GAN, actually we have two generators and two discriminators. Here G is the generator and F is also a generator, and Dx and Dy are the discriminators, and the X and Y are the input and the output. So given a X image, and it will get you will get a Y image. It is the approximate image, and then from there you will get again this reconstructed X image. So you will try to find this cycle consistency loss in this case, and try to minimize this loss. So that is that's why it is called cycle GAN. So, and similarly, if you give the Y image, you will get the X image and reconstruct that Y. So you will get that kind of, this is one kind of image to image translation without training the network with the paired inputs. Yeah, these are all. So in one research paper, they have the input winter image is given, and the summer image is generated like this. And similarly, the sunny image is given, a rainy image is generated like this. Another application of GAN is it can nicely perform arithmetic operation on the image domains. That means it is not the actual arithmetic operation, but on the image domain, it is something differently. You are given with the man with glasses, and you are given the man without men without glasses are given here. So it will try to identify the residual image. That's what is published here, learning the residual image for face attribute manipulation. So what is the residual image? In this case, the residual image is the spectacle. So the GAN will identify detect the residual image, and that residual image can be added to any new image. So when you are giving the image with of the women with glasses, without glasses, it will add glasses to that. So that is called the residual image learning, and GAN is also useful for this kind of operation. These are all latest works. Okay, let us move on to the remote sensing applications of GAN. In remote sensing, it is very useful for cloud removal, and it is useful for generating super resolution image from the low resolution image, and for enhancement. So this itself is one kind of enhancement. Sometimes edge enhancement can be done. And image translation, we have already seen aerial image to map image, you can translate. And then these are the very good applications of this. But recently, people started using this for classification, segmentation, and object detection applications also. Those are all largely attempted by convolutional neural network already. But they are trying to use the GAN for using this for these applications. It is trying to improve these applications when GAN is used. So in cloud removal, there is something called Cloud GAN, which is introduced in 2018. And when you have the images with mild clouds, it will generate image without the cloud. And the cloud GAN is nothing but a cyclic GAN. The implementation is a cyclic GAN. We have already seen the cyclic GAN, which has two generators. So one set of image will be with clouds, and another set of image will be without clouds. And try to learn. So it will learn the cloud automatically, because from one set to another, it will try to differentiate what is the difference in these images. It will try to learn that and map onto the other domain. So it's very cycle GAN is used in this case. And in image enhancement, if you are given a low resolution, a low quality image, it will synthesize, the generator network will synthesize a high quality image. And but before that, you have to train with low quality as well as the high quality images. And slowly it will, when a new image is given with low quality, it will try to synthesize the high quality image. And in another application, it is used for hyperspectral image classification. So it is in 2018, it is published, and this network is we're giving the hyperspectral image, but not directly the hyperspectral image to the network. You have the generator and you have a discriminator here, and the inputs or the principal components extracted from these hyperspectral images. So it will be a lower dimensional image. So they extracted the 10 principal components, and that will be given for training. And the generator, when a new input image is given, then it will again extract this fake data, which is the principal components. And the output is also, you have the input as noise as well as the class input, because it's for classification. So obviously you have to give the class information also. And the output of the discriminator also, you have not only this real and fake information, but also we have the softmax output. The softmax output is for each class, you will have a neural output unit. So it will give the probability that a particular input belongs to a particular class. So whichever gives the highest probability, that will be the class to which the input belongs to. So this is one kind of application, the hyperspectral image classification. Then building segmentation using building segmentation is another application in remote sensing. There is a very recent application in 2021. It got published in Remote Sensing Journal. Here they are using something called O-GANs, which are called orthogonal GANs. So one GAN, there are two GANs here. One GAN is trying to learn the buildings from the image, and the other GAN tries to learn the background. That's why it is called orthogonal GANs, because one GAN is trying to learn one component in the image, and the other GAN tries to learn the other component in of the image. So when these two orthogonal GANs are trained, then when a new image is given, it extracts the building information from it. So more details are available in all these papers. So these are some results of that orthogonal GANs. So you are given the aerial image, and this is the ground truth, just for verification. But actual segmented buildings are shown here, and it also categorizes the building also. It not only extracts segments the building, but also performs the categorization of the building, whether it is they are the small buildings or very tall buildings, or some go downs like that. So that kind of category also it is giving in this case. And there is another work where this GAN is useful for this object detection. Those are all recent work, all this classification, object detection. So they use edge enhanced GAN and a detector network. You must have seen the detector network in object detection network, object detection thing. So those are all like YOLO and SST. Those are all detector networks. These are convolutional networks, and with detection also attached to that. So here, what they do is from the low resolution image, they try to detect the small objects. So they have something called edge enhanced GAN. So it generates the super resolution image. The GAN, the main purpose of GAN here is to generate the super resolution image from the low resolution image. So once the super resolution image is generated, then you can easily attach the detector network for detecting the objects in the image. So during training, the generator is given with the low resolution images and discriminator with high resolution images, and the detector detects the objects on the super resolution image. So the network looks like this, where you have a bigger block for generator, but it consists of a small generator network, actual generator network, which converts the low resolution to the intermediate super resolution image. And then on the super resolution, intermediate super resolution image, this is given to the edge enhancement network, where the edges are enhanced, and you will get a super resolution image with the enhanced edge, and that is given to the discriminator and detector. That is given to the detector actually. Okay. And there is a discriminator also. That is, this discriminator and the generator network, they are meant for generating the high resolution image from the low resolution image. And this edge enhancement network will take that high resolution image and enhance the edges in that, and give the super resolution image, which is very much useful for detecting the objects using the detector network. So this is the edge enhancement network. This is it's not a GAN network, but we have already seen the GAN. There is one edge enhancement network where the input is the intermediate super resolution image. This is a high resolution image, but the Laplacian operator is done on that to extract the edges, and that edge is after improving the image, that edge is getting added to that, and you are getting a super resolution image with enhanced edges. So for core detection on the aerial image, it was used because the objects are very small, and this is the low resolution image where it's very difficult to find out these cars, but this low resolution image is transformed to the super resolution image by the generative adversarial network, and on this network this detector is applied to do the detection. So you must have seen the detection network yesterday, and so that detection is just placing a bounding box over the object. That is one kind of detector. All this YOLO and SST, those kind of detector networks, they put a bounding box over the objects. So when coming to the implementation of this generative adversarial network, there are variety of software available. Most popularly used ones are MATLAB, and then the Python libraries. So all the other networks are implemented with these softwares. And so in MATLAB, you have the dedicated toolbox, deep learning toolbox, and in the Python libraries, you have this TensorFlow, which was the basic library, which is an end-to-end open source machine learning platform, and the Keras is built over this. It's a wrapper built over that TensorFlow. And there is one more called PyTorch, which is a wrapper built over the Torch library. So these Python libraries are popularly used for the implementation of this generative adversarial network and any other deep learning networks. So there is a MATLAB code available. You can even work on that. You can just try it out, where the real images are given, and when the noise, this is the basic GAN only. So in the basic GAN, you have the noise to the generator, given to the generator, and it will generate the image which is close to the real image. That's what we have seen, and the discriminator will try to classify whether the input is a real image or a false image. So both the discriminator and the generator network, they have a 3-level network, convolution network only. So with convolution, batch normalization, and ReLU, all these layers. So it's a 3-layered network, and this is again a 3-layered network. And the implementation is available in this. The code is available here. If I share the slides, then you can easily check the code, and if time permits, we can take a walkthrough of the code, but it's available here. And this implementation, you have the dataset images or some flowers, just flowers are given. There is no class information given, but just the dataset has images of the flowers, and the generated outputs looks like this. They are somewhat close to flower, but not that. Maybe it takes more iterations to generate, or you may need a better network also. The generator and the discriminator should be a better network. And you also have TensorFlow tutorials, and in the tutorial you have many sample codes for different deep learning networks. So you have this as a sample code for training this deep convolutional GAN. The short form is DC GAN they call. It is just both the generator and the discriminator networks or convolutional neural networks. And this is used to generate the handwritten digits. So, and the code is available here. And we have already seen that handwritten digit before, that same thing. So the data set images or these kind of images, they are just black and white images with handwritten characters on it. And the noise input to the GAN, it is a basic GAN only. So the noise input is like this. If you give the noise input like this, then you will get the generator after training, it will give the images some similar to this handwritten characters. So these are some outputs. So after one training epoch, the output looks like this. You don't find any handwritten character here, but after 10 epochs of training, the generator output is like this. And when you increase the epochs, you can see some better image. But after 50 epochs, you can see some the outputs close to the handwritten characters. But it may need more training to get a very good image. So there is another implementation of cycle GAN implementation. We have seen what a cycle GAN is. The cycle GAN has two generators and two discriminators, and it can train the unpaired inputs. So you can give just zebra images and a set of zebra images, and you can give a set of horse images, because we cannot have exactly the paired image in this case. The zebras and horses are completely different. But so you will give the zebra images and you will give the horse images, set of horse images, and in the cycle GAN, if you train the network, both discriminator and the generators, if you train the network, then if the input image is zebra, then it will give horse. And if the input image is horse in the another network, because it has two sets of network, two sets of generator and discriminator networks. And the architecture is because it is taking the input as an image and outputs again an image. Your architecture will be an encoder decoder architecture, where the encoder is nothing but you will have the pooling layers in the encoder. There is two pooling layers is downsampling layers. And so your feature maps or the size of the feature maps keeps on decreasing, and then you will get an encoded feature map here, and then there will be upsampling to get the decoded. So whatever the input image, you will get another output image of the same size, but of different nature. If the zebra image is given, then the horse image will be the output. But the discriminator in this case is, the discriminator is just a classifier. So the discriminator takes only an image, one image, and it will give the output as the, it is just a convolutional neural network with two classes as output. One is the real and another one is the fake. So it is a convolutional neural network with the feature maps. It extracts the feature maps, and then there will be a fully connected layer and whose outputs are two output units. So you will have the real and fake classification. So that is the discriminator architecture normally. So this there is a competition, Kaggle competition available where the code is available here, and here what they do is to build a cycle GAN that generates 7,000 to 10,000 monet style images. Monet style is the one kind of painting. So the inputs are real photographs and the outputs are the paintings like this. And we have these two are the popular references for the generative adversarial network. They are all, it is Ian Goodfellow is the person who designed this network. So in 2014, it was published here in one of these conferences. It's a popular conference. And he has also written a book on deep learning where you can refer to this generative adversarial network in more detail. There are many other books also, a few other books, Charu Agarwal and other books, Nielsen. They also have this generative adversarial network in detail, but it is relatively a recent network when compared to the convolutional neural network and recurrent neural networks. Thank you. If you have any questions, please post.
Thank you, madam. We'll just wait for a few minutes to receive the questions in the chat box. You can also see. We are just waiting to get the questions. Presently, there is no questions in the chat box.
And there is one question. What is the difference between CNN, RNN, and GANs? Could you enlist the main points? Very good. Yeah. They all are different types of networks. CNN is the pioneering network which was developed long ago, which is mainly used for classification, convolutional neural network, classification of images, CNN. And RNN is recurrent neural network. It is mainly for processing the time series. I need not be images, it can be other time series data also. So when there is a temporal, when you want to extract the temporal features out of the data, it can be image or it can time sequence of images or time sequence of any other data, then RNN is very much useful. CNN is mainly used for, the input is mainly image, but RNN, the input may not be image. It is a time series. And GAN is generative adversarial network. The other two networks, they won't generate images. It will only classify. They both classify. And but generative adversarial network is a different type of network where you have two networks competing each other, and they are used for generating a new type of image. That is these are the main differences. And the next question is, can GAN be used for video analysis? GAN be used for video analysis? Yeah, it's a good question. But for video analysis, normally time series networks are very much useful. Recurrent neural networks and transformers. Nowadays, we have something called vision transformer. Normally, the earlier transformer networks like BERT, they were used for natural language processing, where we transform one language to another. It's a time series data, natural language processing, and but GAN is so far it is not. I have not found anything for video analysis to extract the temporal information from the images, but I think we can explore that. How backpropagation is, 1 second. Session is going on. References to learn more about GAN. Ian Goodfellow is a good reference, but there are other books. If you want to know the basics of GAN, books are good, but very recently Charu Agarwal is another book. Ian Goodfellow and Charu Agarwal, they both are recent books, and from that you can get the basic information about GAN. But if you want to learn the variations of the GAN, there are through the references only we can learn. I have listed the references in the slide when I go through this conditional GANs and other type of GANs, image to image translation, so cycle GAN. So all of them have the reference listed below. So when I share the slides, it will be useful. Those. So GAN is actually it is very contemporary architecture. So it is being developed by researchers. Then how backpropagation is different in RNN compared to ANN. Okay, in recurrent neural network, it is again a backpropagation learning algorithm only, but it is the backpropagation through time in recurrent neural network. They do the backpropagation through time. They sample for few samples. They take the loss and average it over, and then update the weights. But the general ANN, which is a shallow neural network, artificial neural network, is I think you mean the shallow neural network, in which we don't have any time information. We give the present image, sorry, not image. Artificial neural network can be presented with the input vector. So if you give present the input vector and the output, the pair, the target output, then you will get the error after passing through the layers. You will get the error output, and that will be backpropagated and used for. But in RNN, the backpropagation, again, it is a backpropagation only, but it is a backpropagation through time. So you will be giving the samples, time series samples, but not the entire sequence. We can chunk the sequence and give the chunks of sequence and get the average error for adjusting the weights. Yes. Apart from photo manipulation and photo detection, where can we use GAN? Photo manipulation is one application, but I have listed many other applications in remote sensing also. In remote sensing, it is useful for cloud removal and enhancement, because when you have the low resolution image, then you can get the super resolution image by means using the GAN, because GAN will try to generate the super resolution more meaningfully. So that is, we have listed, we have seen a few applications in remote sensing also. And photo manipulation is not a remote sensing application. In the other domain, I have given the application. And do we need GPU or TPU to build GAN networks? GPU would be sufficient to build GAN networks. These are the questions from the participants. Okay, thank you.
So thank you, madam, for considering our request for delivering one talk in this 5 days machine learning to deep learning program. And I know you have been there 2 years back when we have conducted in-campus program that was again 5 days regular marathon program on machine learning to deep learning. And I've seen your whole day taking classes and demonstration. And I'm really thankful the way you have taken the today's topic on GAN, talking a different form of deep learning as a GAN picture you have given, types of GAN you have covered, image to image translation application, remote sensing applications like cloud removal, enhancement, classification, application in hyperspectral data for classification, building segmentation, object details extraction, and cycles of GAN. That's a further advanced form of GAN you have covered. So I'm really thankful, and I hope you will have association and support to us in the future also.
Yes, sir, definitely.
So on behalf of IIRS, again, I thank you, madam.